Have you ever stopped to think about what a dripping faucet, the blood flowing through your veins, and a jumbo jet soaring through the sky all have in common? Well, it's all governed by the hidden physics of fluids. These are the invisible forces that literally shape our world, and today we're going to pull back the curtain and see how they work.
So here's what we're going to cover in this explainer. First, we'll nail down the basics. What even is a fluid? From there, we'll dive into pressure, how it changes with depth, and that'll lead us right to Pascal's incredible principle. Then we're going to unlock the secret of buoyancy, why stuff floats. After that, we'll see what happens when fluids get moving, and we'll wrap it all up with Bernoulli's amazing equation that, yes, explains how airplanes fly. Let's jump in.
All right, first up, what is a fluid? We have to start with the absolute fundamentals of matter that can flow. Okay, let's start with a simple question. You've got water, you've got the air you're breathing, and you've got thick, slow-moving honey. What on earth do they all have in common? Well, in the world of physics, they're all considered fluids.
So what does that actually mean? A fluid is basically any substance that can flow and will always take the shape of whatever container you put it in. Now, the key phrase here is that it cannot withstand a shearing stress. Okay, think of it like this. If you put a big book on a table, you can push on the top cover and slide it. That's a shearing force. But try to do that to the surface of water in a bucket. Your hand just goes right through it. The water flows. You can't stack it. And that's the big idea. It's why both liquids and gases get lumped together under this one banner, fluids.
Now, when we start talking about fluids, we have to talk about pressure. It's one of the most important concepts. Take a look at this little sensor here. When you stick it in a fluid, the fluid pushes on that piston inside, which then compresses a spring. By measuring how much that spring gets compressed, we can figure out the pressure. It's really just a measure of how much force a fluid is pushing with on any given surface.
And here is the beautiful, simple formula for it. Pressure, which we call P, is just the force, F, divided by the area it's spread over, A. It tells you how concentrated that push is. But here's a really important detail. At any point inside a fluid that's just sitting still, the pressure is the same in every single direction. It doesn't have a direction itself, which is what we call a scalar. The force it creates has a direction, but the pressure itself is just a magnitude.
Okay, brace yourself for this one. The air all around us, the atmosphere, is a fluid, right? And it is pressing down on you constantly. How much? Well, the force on the top of your head right now is about 4,000 newtons. That is the equivalent of having almost 900 pounds sitting on your head. So why don't we get crushed? Because the pressure inside our bodies is pushing outwards with the exact same force. It's a perfect balance. Kind of mind-blowing when you think about it.
All right, so we live our lives under this immense pressure. But what happens to that pressure when you go deeper into a fluid that's just sitting still? Let's explore the forces in fluids at rest.
You know, anyone who's ever dived to the bottom of a pool knows this feeling. The deeper you go, the more pressure you feel in your ears. This is called hydrostatic pressure. And the reason is simple. Imagine you're standing in a library and someone puts a book on your head, then another and another. The more books, the more weight you feel. It's the exact same thing with a fluid. The deeper you are, the taller the column of fluid sitting on top of you, and all of that weight is pressing down. This equation sums it up perfectly. The pressure P at any depth is just the pressure at the surface P naught, plus the fluid's density ρ times gravity G times how deep you are H.
This idea leads us to this incredibly elegant rule from the brilliant Blaise Pascal. Basically, he figured out that if you have a fluid in a closed container, like a water bottle, and you increase the pressure somewhere, say by squeezing it, that extra pressure is instantly transmitted, completely undiminished, to every single part of the fluid and even to the walls of the container. You see this every time you squeeze a tube of toothpaste. You squeeze the middle, and the pressure makes toothpaste come out the end. That's Pascal's principle at work.
And here is where Pascal's principle becomes like a superpower. This is a hydraulic lever. Remember, pressure is force divided by area. So if you apply a small force to that piston with the small area, you create a certain amount of pressure. Pascal tells us that same pressure shows up over at the big piston. But because the big piston has a much larger area, that same pressure creates a much larger force. This is the magic that lets a hydraulic jack lift a 2-ton car with just a few easy pumps.
Let's keep building on this. We know pressure pushes on an object from all sides, and it gets stronger with depth. So what happens when that pressure pushes up? We're about to dive into the secret of buoyancy, the reason things float.
So the story goes that Archimedes had his famous eureka moment when he got into his bathtub. What he realized is what we now call Archimedes' principle. When you put an object in a fluid, the fluid pushes up on it. We call this the buoyant force.
And get this, the strength of that upward push is exactly equal to the weight of the fluid the object pushed out of the way. It happens because the pressure on the bottom of the object is slightly greater than the pressure on the top, creating a net force pushing upwards. So you can think of floating and sinking as a simple tug of war. You've got gravity, the object's weight, pulling it down, and you've got this buoyant force from the fluid pushing it up. It's a straight-up battle. In the picture on the left, the stone's weight is stronger than the buoyant force, so it sinks. But on the right, the buoyant force on the wood is much stronger than its weight, so it rises to the surface.
So what's the secret to floating? It's all about finding a perfect balance. An object will float when that upward buoyant force exactly equals its own downward weight. This means a floating object pushes aside or displaces an amount of fluid that weighs the exact same as the object itself. And that is how a gigantic ship made of steel, which is obviously way denser than water, can float. Its huge hollow shape allows it to displace an enormous weight of water, enough to perfectly balance its own incredible weight.
Fantastic. We've pretty much mastered fluids when they're sitting still. But of course, fluids don't always do that. So what happens when they start moving? Let's shift gears from the calm world of hydrostatics to the exciting world of fluid dynamics.
Let's start with a question I know every single one of you has experienced. You're using a garden hose, and you put your thumb over the end to cover part of the opening. Why does the water suddenly spray out so much faster?
Well, the answer lies in something called the equation of continuity. For a fluid we can't compress, like water, it's a simple idea. The amount of fluid that flows into one end of a pipe has to be the same amount that flows out the other end in the same amount of time. You can't create or destroy the water inside the pipe. What goes in must come out.
And here's the math that explains the garden hose. It says the cross-sectional area of the pipe, A, times the fluid speed, V, is constant. So A1 times V1 at one point equals A2 times V2 at another point. So think about it. When you put your thumb over the hose, you are making the area A much smaller. For the equation to stay balanced, the speed V has no choice but to get much, much greater. Simple as that.
All right, we've made it to our final section. And this is where things get really interesting and maybe a little counterintuitive. We're going to tie speed and pressure together with Bernoulli's famous equation.
This right here is the absolute key takeaway from Bernoulli's principle, and I want you to really let it sink in because it can feel backward at first. In a moving fluid, where the speed is high, the pressure inside the fluid is low. And where the speed is low, the pressure is high. Say it with me. Faster flow, lower pressure.
This diagram shows it perfectly in action. You see the fluid flowing around that cylinder? The lines, which we call streamlines, have to get squeezed together to get past it. Now, we just learned from the continuity equation that when the area gets smaller, the speed has to go up. So the fluid is moving faster as it goes around the sides. And according to Bernoulli, that faster moving fluid has lower pressure than the slower moving fluid farther away. That pressure difference creates a force, and that is the fundamental secret to aerodynamic lift.
And this is the full equation. I know it looks a little scary, but it's really not. What you're looking at is just the law of conservation of energy, but rewritten for fluids. Let's break it down. That first term, P, that's the pressure energy. The second term, 1/2 rho V squared, that's its kinetic energy, the energy of its motion. And the last term, rho Gy, that's its potential energy from its height. All Bernoulli's equation says is that if you add up these three kinds of energy at any point along the fluid's path, the total is always the same. It's constant. So I'll leave you with this final thought to connect all the dots for yourself. An airplane wing is specifically shaped so that the air has to travel faster over its curved top surface than it does across the flatter bottom surface. Now that you know that fast-moving air has lower pressure, can you start to see how that shape creates the incredible upward force of lift that allows a massive plane to fly?